After we have discussed the basic concepts and some methodologies, let's now move to several kind of real-world examples, more complex examples to give you a sense about how to formulate a problem and solve it. The first case study here is about production scheduling. So I suggest you to have a look at this website of Groovy. It has a lot of very good examples discussed there. This is also one of the example to use optimization given by the examples groovy.com. Groovy is basically optimization solver, but their website provides you many interesting examples that can be useful in your study and application. So this case is about production scheduling for a pulp and paper factory. So this factory uses wood as a raw material to produce different types of paper, cardboard, and pulp. So it's multi-product with a same raw material. Each product has a cost and can be produced at a certain rate. So it's important to read the problem statement and convert these words to some mathematical representation to the symbols, parameters, variables you will use to the optimization. Okay, let's read it first. The goal is to decide, given the demand, the amount of each item to produce in order to maximize the profit. And it's also given that we can run the factory beyond the time limit. So it's certain time limit given here. But if we pay for the overtime, so if within the time limit, it's no additional pay. It's just one total cost of B for the machine time. But when you have overtime requirement, if you need to run the factory more than 10 hours per day, for example, it's time limit here, you need to pay additional cost for this time, additional time you spend. All right, so that's the problem statement. And if we want to optimize this problem, how do we formulate it? Okay, so first think about what is the variables you want to decide. What are the decision variables to give you the problem? So we want to say the amount of each item to produce. Okay, each item, the amount. So it can be a continuous variable for amount x. Right, so you can put x as a variable here. And we know that if you look at the website, you know the given conditions. It gives you the cost function is given using this curve here with constant in the first phase divided by time limit t-lim and a straight line, a linear function in the second phase. So think back to this problem formulation. What is the objective function? Our goal is for the plant operation to maximize its profit. Right? If you think about the objective function, we want to define the profit to be maximized. What is a profit? A profit for a company, for a plant, equals the revenue, which means the return from the product minus the total cost. Okay, so this is a profit to be maximized, which equals the revenue R minus the cost C. Well, for the revenue, because it's a collection of products, so we know the I is a total I belongs to P is a total product. And for each product, we define the RI can be the resources needed, can be the revenue for each product. This is revenue, right? So it can be the selling price or revenue of each product multiplied by the amount produced. So X is the amount of each product. So this is the revenue. Well, the cost is already given, right? So this is a cost function we are given. So for what is given, you can look at this example. Go to this website, Group A website, to see more given conditions for this example. Therefore, we can formulate in this way. Then the constraint, we know that for the time constraint, we know it's a total like a Tmax. You cannot produce more than 24 hours per day if it's giving a maximum point here. So know the total time for the product cannot be beyond this total machine time. Therefore, you have this T is equal or smaller than Tmax. Well, T is calculated for all the product. For this each amount, you know the production time required. Because here, the PI is defined as the hourly productivity, as given this example definition. So it means how many or the amount of product produced for each time unit, or here is each hour. So this hourly productivity multiplied by time will be the total product. So if you want to calculate the time, you should use the total amount of this I product divided by the hourly productivity and get the time allocated for this product. So here it is not as straightforward, but based on how you define these parameters. So P is given as the hourly productivity. If you see in this problem formulation, then we use the amount divided by P gets total time. Well, total time is smaller or equal than Tmax. And also for each product, it has been a non-negative value equal or larger than 0, and it has a maximized amount. Like for each product, maybe based on the capacity or the market demand, this Li is imposed. This is a problem formulation. If you look at the website again, it gives you a direct interactive phase to see based on different parameters citing the time limit and the hourly productivity for each product. Okay, so you see for all those products are given here, and you will be able to adjust the parameters to see what is the optimal results obtained. So the parameters, you can change the total hours, you can get the optimal value for the profit. So this is a very good example. I suggest you to have a look at this. We may use this example again in the later part to review the linear programming or more constraint optimization problems. We also have more relevant problems that's to chemical and biomolecular engineering, for example. So this is quite a complex example. It's also from the NUS one case study on the optimization website. I put it here for metabolic engineering. So think about a biological system, a human cell, how it works to do the metabolics engineering. It takes all the nutritions like carbon cells, nitrogen cells, and all these input, well, to give the output of the chemicals or some waste and some biomass. So this is a typical pathway for like a microbiome-based fermentation or some reaction system. So it seems very complex if you see how to build up a model to study such process. It is quite advanced level optimization problem already, but we want to give you a sense here how to solve this. You can form this reaction. Although it's biological, you can also use the chemical concept to form this reaction of your input A, B, C, D as an input element with certain coefficients So this will be your reaction. So from A plus B to C and D as a general equation. This can be the flux balance analysis. The key thing is about those parameters based on the different reactions. You can have multiple reactions, right? It's not just A plus B towards C and D. You have a lot of the main reactions, set reactions. So you have a series of matrix to indicate the reactions. Like if you write in this way, if you're familiar with the matrix operation, you can write your first reaction and reaction 1 to reaction M. So this is how you formulate this matrix-based optimization model. And this is steady-state material balance. This is a biological system, but in the chemical process, you can also formulate the chemical reaction material balance. This balance will here again become your optimization constraints because it's equations, equality constraints. So this basic optimization, you got the constraint to describe the system, and your goal is to maximize the valuable product. So V are the flux output you want to get with some coefficient C. So it can be the value. So value multiplied by the amount you want maximize the total value for the output. Well, for each of for each of these my types, it gets certain lower bound. We use LB to indicate lower bound, and the maximum value upper bound UB. So this is a basic problem formulation. We are able to describe this corresponding to the reactions in the network. You get the output of the metabolites to obtain the final valuable product. So your decision variable here, all the V you will be able to get from the reaction network. Okay, so this problem then you can use some standard tool to solve. Then you will become a biological scientist to use model to study the very complex biological system. But of course, this has been simplified. This is just by assuming the biological system follows the material balance, but more sophisticated characteristics are not captured. So when you do the modeling, you need also to consider what is the complex level you will use. So based on this, a lot of assumptions need to be made. If you make the model too complex, there will be no solution to your optimization problem. With some case studies we describe. And in the last part, I want to show you some research examples here we are doing especially in my research group. As the picture shown here, we use data, models, process, and system on different scales. We can all formulate the problem as mathematical models and further optimize it. So if you're interested in the last part, it will be more explorative process to give you some more advanced optimization problems. So our group is called a Smart System Engineering group. Why do we call it smart? Because we are able to use abundant data and computing techniques of modeling, simulation, and optimization to solve many of the real-world problems through a multi-scale approach. Singapore is now building a smart nation from the national strategy. Similar to the concept of smart city in many cities around the world, we are having more digitalized technologies, the network of data to provide sustainable and resilient progress. When we optimize the city structure, or when we design and operate the city structure, optimization is very important to play a role. And we also, as chemical engineering major students and researchers, we study a lot about future human well-being through energy, healthcare, manufacturing, and many of the relevant aspects. Like energy systems, if you formulate them as energy flow, it's supply and the demand matching, how you satisfy all the demand with efficient resource supply. That's a typical optimization problem. And for the healthcare, we have showed you the biological problem before, but also it's a lot concepts that can be even strengthened through the bioinformatics or optimization techniques to improve both the discovery of new healthcare problem solutions or the pharmaceutical manufacturing. Also, our group has now conducted a lot of the data analytics, machine learning to the accelerated manufacturing of materials and different chemicals. Our goal is to accelerate the material and industry innovations using data and optimization instead of the previously commonly used strategies in lab in plant, which is trial and error to design the system experiment. We'll be able nowadays to use the abundant data and optimization to optimize the process, to dig into the process using machine learning to find the inherent rules that was not easy to be identified by human brain, but a computer can help us to accelerate the whole process. So that's an overview of our some problems we do in the research program. If you're interested, you can also work with us with some advanced level optimization problem. For example, in the smart city development, we have the sustainable planning of energy, water, food, waste nexus. How we do that is to model the whole environmental system, natural system through a holistic platform to support the ground level planning of multi-sectors. So we are able to map those results on the map layer, and human behaviors is also a key part to be modeled. You can use mathematic models to describe like human behaviors. So we use some agent-based modeling to simulate and forecast resource demand based on spatial and temporal scales. And then the resource optimization network for all different sectors, because these sectors nowadays are interlinked with each other. When you study the energy system also provides a lot energy went to the food industry or to the water distribution, and the water is a necessary component for the energy production or supply. Also, the food and water, they are closely interlinked, and all sectors produce waste. Waste need to be treated, and waste can be recovered for energy, water, and even more resources. So this resource network optimization will consider some capital expenditure, operational costs, and environmental impacts to optimize the overall framework network. So this is quite advanced level research questions. You don't have to understand the details, but I want to share with you some of the work we are doing here. If you do have a strong interest, you can conduct some research projects or collaboration with us. You can also use these concepts in your individual project, and the group project will also be linked with some of those concepts in the ongoing research. If we focus on the energy system, for example, so nowadays we use a lot modeling tools to study the energy systems. Cities, like Singapore, those mega cities or smaller cities, consume almost 80% of the world's energy. So this is a huge problem to study, to focus on how we can provide sustainable energy to power our life, our commercial sector, and our industry. So you may don't know what the electricity you are using daily is from, or your have you look at your electricity utility bill of your family or apartment to see the total flow. So here we use some of the charm to show the energy flow from the initial supply. So it can go to the electricity and divide it to all different demand field for different industry and the residential transportation use. So this kind of figures are very nice realization of the numbers. You can also have a matrix about the input and the output of the flow of energy. And then these numbers can be the parameters. Remember the optimization model need a lot of numbers as parameters to describe your equations of energy balance. So we rely on natural gas in Singapore a lot, right? So we understand how the gas is imported and generate electricity to further supply demand. And then we can consider the cost, economic cost, environmental cost, stability metrics like the carbon footprint, water footprint, and even the social impact for the whole energy system to obtain a circular economy with a novel integrated energy system. So in week 3, we will have a guest lecture from the industry who is very experienced to tell you more aspects from the applications in industry of the information technologies and optimization. Then the final group project will possibly be based on what we have talked about, all the context. We will give you some solvable problems, but also some freedom to develop your own solutions to design this circular economy for the whole city level or for the plant level. So this will be very important for your understanding how to use optimization to solve our human beings' future, to solve the sustainable development issue. And here I also show you one example of the optimization formulation. If you just see the whole story, it's difficult. You link to how to really write down the equations and put the numbers in. So this is some case study we did for energy system optimization. Still the same, if you have the cost function considered as a total cost, here we use an economic objective that considers operating cost for a system and the environmental cost. So we turn the cost term to money value and adding some coefficient for the currency exchange or for the lifetime. For 20 years, you multiply by 20, or for some weighting factors, you want to emphasize environmental cost more, so you put a coefficient here. So that's how you design the cost function. And then for the constraints, those are don't worry if you find this very challenging. This will be the end goal for your learning of this class. So you may be very confused at this stage to understand the model, but in the second half, after the recess week, we'll start to do the group project. This will be more clear. You will be able to write down your optimization problem similar to this, or even more comprehensive, or tailored to your own problem statement to get an understanding. So here, just want to show you some examples. Okay. So in the continuous domain, you can also write the cost function integrals through some time, or you can, in the discretized time domain, it can be the every year's cost. So it's yearly costs, hourly costs, summed together. So this is commonly used. If you write it as an integral, it's very difficult to solve. But if you write it as a summation by time, you will be able to get this objective function. And for a constraint here, because for energy systems, if you want to bring more renewable resources of wind energy, solar energy, together with the energy storage and the traditional resources, your target is still you must meet the energy demand. So this demand-supply balance is added. The supply will be equal or larger to a demand. But if also in this research project, we propose a new concept. So we have this soft constraint. Instead of saying the demand must be satisfied, we put this unmet demand. So this unmet demand will be equal to the total demand minus the supply, which is the unmet part. And we want to minimize this part with a coefficient gamma. In this way, we are able to bring more flexibility to this formulation, but ideally in optimization, it will drive this item to 0. But if really it's economic to sacrifice certain demand, this is also feasible to solve the problem. And for each of these generation components, it normally has its upper limit, lower limit, as we introduced before, lower bound and upper bound of each variable. And also there's some constraint imposed here, so the delta, like the change, because it's time dependent. So from this hour to next hour, the change cannot be so big. You cannot jump from 0 to 100, cannot immediately from Singapore to China. So you still need this constraint for this difference value. Therefore, we have a time index for the delta term in between should be smaller than this upper value. So this is a very complex formulation, and we're able to use tools to solve this. And in your project later, you can try to form such kind of optimization problem. Okay, so that is an overview from the lecture 1, the introduction. We have given you a lot motivations, hopefully, to see why optimization is important and promising to do. And we also go through the history of optimization, how the commonly tool we used to solve problems, and then the cost requirements, followed by some basic type like linear programming, least squares problem, and the convex optimization. In the end, we give you some comprehensive examples. So hopefully this first lecture give you a basic sense. All the content we will cover in detail later, so don't be stressed if you don't understand all the terms we described here. But it's good that you see the whole picture and start to look at your interest point and find the synergies with your project and with your work, with your research. Okay, so thank you for your attention in lecture 1. Thanks for your patience through the whole lecture. Hopefully the video is helpful, so you can look back again if there's some points unclear, and I appreciate your feedback. I have my contact information on screen, so please feel free to drop me an email or talk to me on Saturday open office hours or the lecture time. All right, so see you next week in the classroom. Bye.